Okay. mm, so my this lecture is on plane diffraction grating, and I'm going to discuss on transmission grating. Okay, so before we start, let us see a pictorial diagram of how the grating looks like. So these are the plane diffraction grating. Okay, this is uh, the glass plate on which some parallel rulings are made by some materials, and those rulings are basically very fine opening through which the light ray can pass, and there will be some opaque region on which the light ray does not transmit through. And this grating has 600 lines per millimeter, as you see in this picture. And there is another type of grating which is 1000 lines per millimeter. So depending on the number of rulings, this grating will uh, give us different diffraction photographs on the screen. Now if you look at the CD, that is compact disc, in a tilt manner, you are tilting a disc to a certain angle, and you look through the disc, keeping it under the light, then you can see there will be some rainbow color on this CD. And this rainbow color is due to diffraction from the fine rulings made on the compact disc. Okay, apparently the CD looks as a planar one, but there will be different a certain amount of rulings, very fine rulings are made on this compact disc, so it is look like this. So if some light rays passing through this grating, uh, if that is monochromatic light, then there will be certain amount of maxima minima that are present due to diffraction. As in case of single slit, in my previous video lecture, you see that there was only the diffraction maxima minima. But when the number of slit increase up to 2, so instead of single opening, you are using 2 opening, then 2 rays are coming from that 2 opening, and at the same time the 2 single slit or at the same time, in addition to diffraction pattern, there will be interference, as you see in case of double slit. Now if you increase the number of slits to n equal to 3, n equal to 4, n equal to 5, then what happens? So grating is basically the diffraction through n number of slit, and the n is, in this case, this n will be 600 lines per millimeter, and in this case 1000 lines per millimeter. Okay, so at first I want to see what happens when a plane diffraction grating is illuminated by a monochromatic light. Obviously they are parallel. Okay, now the source which I use in laboratory for illuminating the grating element, or for the grating for the diffraction experiment, that is sodium light. And this sodium light, as you know, that it has two very close lines, okay, of 5/8 5893 and 5896 angstrom. And as sodium lamp has these two very close line, it produce the diffraction pattern, and we can assume that that sodium light is to certain extent a monochromatic one. Okay, so sodium uh, uh, yet it has got two very close lines, so in approximately we can consider that the sodium is a monochromatic light source. We can also use the laser source to illuminate the grating and observe the diffraction pattern, because laser source is also a monochromatic light source. Now come to the experimental arrangement, that is how the diffraction pattern is experimentally observed. So this is a sodium vapor lamp in which we can place a sodium tube. Initially I have showed you the construction of a tube, and this is a collimator to make this sodium incident light as parallel one, because there is a convex lens placed in this collimator, and this is the tabletop on which I place a grating. In experiment you can see that this is the grating which placed on the uh, table, and there is a vernier scale which is seen through this transparent region. There is two vernier scales which is calibrated in degree, and there is a telescope through which I can observe the spectrum that are coming through this grating element. Okay, so these are basically the experimental arrangement, that how we can measure the diffraction in the laboratory, and this is how we can measure everything. So uh, this instrument is known as spectrometer. So by the spectrometer we can measure the diffraction experiment. Okay, now if you look through this telescope, how the spectra looks like. So these are basically the grating spectrum which I can see through the telescope. The central fringe, where the central fringe for m equal to 0, all the light rays are coming, and all the colored light that are basically uh, incident at the same place. So we get a yellow light, that is central maxima, and in the both side of central maxima we get the first order maxima here. Centrally there is yellow line, and there will be alternative red, from red to violet one. So m equal to -1, that is also first maxima in the on the right side, and this is first maxima on the left side. And we can also get the m equal to 2, m equal to 3, etc., depending on the n, that is lines per millimeter, it is rulings of the grating. Okay, now so practically the grating spectra, if we observe through the telescope, we have seen this kind of grating spectra through the telescope. Okay, now if you use a laser source instead of sodium light, how the spectra look like. So this is the laser pointer, that is the holder of on which the grating is placed, and you can observe the principal maxima here m equal to 0, and the first order maxima, second order maxima. So those things are looked. And on the screen you can see that this is laser source, this is the diffraction grating, and you have got some spots, that is for maxima, and within that spot there will be some minimas are there. Okay, so these dark region, they are basically the minimas. Okay, so uh, either you use the sodium light or you use the laser pointer source, you have got the alternative maxima minima in case of diffraction through a plane diffraction grating. Now come to the part of the theory that how the grating is working. Okay, so let us consider this number of rulings in the uh, very crude way. That is, how can we take the number of rulings? You can use alternative opening and opaque region, that is transparent and opaque region in this way, and some parallel light source, that is AB, that this wave front, that are incident on this plane diffraction grating, and each point on this transparent region that are act as a source of secondary wavelet. Now, as this elemental grating has n number of slits, so number of slit is small in here, and width of each transparent region is opening is A, and the distance between two successive slits, that is this opaque region, is equal to B. So D equal to A plus B, which is known as the grating element. Now if you choose any of this opening in this way and take a small elemental length dx through which this rays are coming, that is P and Q rays are moving, and from central region, if you choose this is m equal to 0, so through the central region OQ rays are moving, and these two rays, they are incident at an angle theta. So the path difference between these two rays is basically P into n, Pn, sorry, this distance, Pn distance, and these two rays are superposed at the point Q. Now let us consider that how this grating act, that is what is the working principle or the theory of grating. Let the wavelength of this light is lambda. So according to Huygens Fresnel principle, each and every point of the incident wave front in the plane of slit may be regarded as a secondary spherical wavelet, as I consider in case of Huygens principle. So each point is considered as a source of secondary spherical wavelet, and this spherical wavelet, they are traveling normal to the slit, and that is focused by this convex lens L on the screen at some point. Okay, let us, this point is Q. Now the wavelets that are traveling through this inclined pathway, they are superposed at the point Q, and those rays which are responsible to create the central maxima, they are incident or they are superposed at the point Q. This is say C, at the point C. Now these wavelets are having some. Okay, so this diffraction, if you look at these things in a very crucial way, you can see that this is basically the path difference between the rays, this delta L, that is d sine theta, and in this case d sine theta equal to m lambda is the condition of uh, maximum interference, okay, which is in case of crystal system you can see that is 2d sine theta, this is Bragg's law. Okay, so d sine theta equal to n lambda is basically the condition of principal maxima, and if these two rays that are incident in the inclined wave, this initial path difference between these rays are basically d sine theta I, and obviously in this direction that will be d sine theta. So d sine theta I plus d sine theta equal to n lambda, that is a condition of maxima in this case. Now if incident rays are parallel, that is in this way, in this configuration, that incident ray are producing the n equal to 0 at the central maxima, that is n equal to 1 first order maxima, this n equal to 2 second order maxima in the upper side, and in the lower side there will be again principal maxima and n equal to 2, that is second order maxima. Now these are the uh, just pictorial diagram of this grating experiment. I have to measure this 2 theta angle to get this value of sine theta. So this theta is very important to uh, for the measurement of unknown rulings, and for measurement of unknown wavelength if we know the number of rulings of the grating. Okay, so this is basically the flowchart diagram, that how you can estimate the unknown wavelength or unknown number of rulings through this grating. Now come to the part of theory, that grating is basically consist of, as is written here, that is parallel, obviously equidistant lines. This is very important, equidistant line that is ruled on a optical plane and on parallel glass plate. Okay, now first consider that a parallel beam of light of wavelength lambda, these are the parallel beam of light that are incident normally on the plane diffraction grating, and those parallel light have wavelength lambda. N is the number of slit, transparent opening is A, and obviously opaque region that have of width B. So A plus B is a grating element. Now the complex disturbance, that is the complex disturbance that are basically moving from point O, that is from this point, and moving towards Q, that have a complex part and a real amplitude. So A is the amplitude of this incident rays, and e to the power I omega t is the phase factor that is incident that are connected with this uh, disturbance. So now as these rays are travel at a of distance x, so if we consider that of these two rays, so these two parallel ray must have some path difference which is of this distance, this amount of distance from this point to this point. So delta L amount of path difference is initially developed for these two parallel rays. As this delta uh, L amount of path difference in this case is equal to Pn. Okay, so Pn is the path difference, and if Pn is the path difference, then the phase amount of phase difference that are initially produced between any two rays which are coming from this point O and point P, that will be twice pi divided by lambda times Pn. Okay, right? You have learned this from interference and diffraction phenomena. As I have said, in case of single slit and double slit, both uh, in those cases, the same amount of path difference is made for any two parallel rays that are coming from any two successive point of the elementary diffraction region. So twice pi divided by lambda into Pn, that is the path difference. Now if you look at the picture, this Pn is equal to x into sine theta. Okay, as you have already know that x into sine theta, so this length, obviously OP, this will be of the length of x. Okay, so this twice pi divided by lambda into sine theta, I can consider this factor as L. So L times x is the phase difference between two waves that are coming from point O and P. Now by reaching the point Q, when these two rays are reaching to point Q, the rays which are coming from point O, that are travel a distance of x in the x direction. So additional kx amount of path difference is produced within that wave. So disturbance at Q due to secondary wavelet, that is I into e to the power omega t minus into kx. Now in this case, this k is equal to L. Okay, so I omega t minus L times into x. Okay, so this path difference, this wave are reaching, so a into e to the power I omega t min into Lx. Now c is the scaling factor which determines that what amount of wave is reaching to the point Q if there is any kind of transmission or sort of something happens in case of primary wave, secondary wave front. So C is just a proportionality constant, and this proportionality constant is depend on the width. So the amount of disturbance that are reaching and that amount of disturbance are responsible to be produced by this elementary length dx must be equal to c times dx into this complex amplitude. So c a dx into e to the power I omega t minus lx. So these are the amount of disturbance that are reaching at the point Q. Now if you consider these things, this wave are coming from each of these slits opening. Now if you consider all the slits at the same time, you can get the resultant intensity or the complex disturbance that are reaching to the point Q due to all slits. So y, that is the resultant disturbance, equal to minus a by 2 to plus a by 2 c a e to the power I omega t minus lx into dx plus d minus a by 2 to d plus a by 2. How this d minus a by 2 d plus a by 2 comes, that I have discussed in case of double slit. So into Ca e to the power I omega t minus Lx into dx plus up to this n minus 1 d minus a by 2 to n minus 1 d plus a by 2 C a e to the power I omega t minus Lx into dx. So these are the total resultant amplitude, resultant disturbance that are reaching at the point Q due to all these slits. So if you consider all these slits at the same time, you can get this amount of resultant disturbance. Okay, now if that is the resultant disturbance, and if you simplify this resultant disturbance, if you integrate this factor, you can get Ca e to the power I omega t minus Lx divided by minus IL. Okay, so for the first case, that is e to the power ILx divided by IL, and the definite integral runs from minus a by 2 to plus. So in for the second term, this integration, obviously the term comes as the same way, Ca to the power I omega t into e to the power minus ILx divided by minus IL, and obviously this definite integral runs from d minus a by 2 to d plus a by 2, and in a similar way for n minus 1 d minus a by 2 to n minus 1 d plus a by 2 e to the power minus ILx divided by minus IL. Now if you put all this term here, you can get the same thing as we get in case of double slit experiment, that is sine AL divided by 2 into AL divided by 2 into CA into small a times this, and the another term that arises due to n number of slits, that is e to the power minus INLD. If you add all these terms, this is a GP series, and you can get e to the power minus INLD minus 1 divided by e to the power minus ILD minus 1 into the power I omega t. Now if you apply the this is the disturbance, that is wave that are coming as a complex disturbance. So the intensity, obviously y into y star is a complex conjugate of this y, and the intensity becomes Ca its whole square into sine square Al by 2 by Al by 2 whole square into the complex conjugate of this term, obviously to the power INLD minus 1 to the power INLD minus 1, and the same way to the power minus ILD minus 1 into the power plus ILD minus 1. So these are the intensity factor that are that happens in at point Q due to the complex disturbance that are reaching to the point Q from different points of total n number of slits. Okay, so if you calculate this intensity, obviously this is sine square Al by 2 by Al square. I can write this term as sine square alpha divided by alpha square, and if you add this term, this will be to the power minus INLD to the power minus ILND into to the power ILND minus to the power minus ILND, and in this denominator comes as the same way. So this will be sine square in beta by beta square, where this alpha is considered as Al divided by 2 and the beta is considered as pi by lambda d into sine theta. So pi by lambda a plus b into sine theta, and obviously the incident intensity, that is I0, which is the undeviated wave that are incident at the point O, that is before the diffraction happens, that is Ca times small a whole square. So as you see here, mainly this disturbance, that is the uh, the intensity is basically depend on the two factors, that is sine square alpha divided by alpha square and sine square n beta divided by sine square beta. So if any of these two becomes minima, then intensity will be minima. That is, if any of these two becomes zero, then intensity will be zero. And in case of maxima, both should be maximum, right? So now in case of maxima minima, let us consider that how can you see all this term, that is maxima and minima. So let us first consider the principal maxima. Okay, now if the slit width A is very small, right? So generally the slit width is small compared to D, right? So if slit width A is very small, then sine square alpha divided by alpha square, that varies in a very smaller fashion. Now the condition of maxima, that becomes independent of sine square alpha by alpha square if A is small or A varies in a small way. And the intensity maxima is solely depend on the factor I2, that is sine square n beta by sine square beta. Just watch this pointer here. So this factor is solely responsible for producing this principal maxima if the slit width is very small. Now if you consider this I2, this factor become maxima if beta is equal to m pi. N is integer, capital N. As n is integer, if beta equal to m into pi, then this factor will be maxima, 0 by 0 form. So if you use this limiting condition, so for beta equal to m pi, I2 becomes limit beta tends to m pi sine n beta by sine beta square. So this is 0 by 0 form. You have to apply the L'Hospital rule and you have to differentiate in upper portion and the lower portion. For upper portion you get n cos n beta, and for lower portion it will be cos beta. So now if you put beta equal to m pi, this will be capital N square. Okay, so for beta equal to m pi, this equation or I2 becomes maxima. So if I2 becomes maxima, the condition is beta equal to m pi and m equal to 0 plus minus 1 plus minus 2 or so on. So a plus b sine theta equal to m lambda, this is the condition of principal maxima here. Okay, now so this is the maxima. Now the intensity, as intensity I2 is equal to n square times n square, so for principal maxima, so intensity will be I0 sine square alpha by alpha square into n square. And obviously this term sine square alpha divided by alpha square, that arises in case of single slit and double slit in the both cases. So this is basically predominantly due to diffraction from any of the single slit. Okay, so n square into the intensity due to single slit, that is basically the intensity of a grating element, right? Now if you consider secondary maxima and secondary minima, now if you look at the thing, as the maxima is governed by solely on this I2, so I2 maybe control the secondary maxima or minima conditions. Now the factor I2 is basically sine square n beta divided by sine square beta, and this factor depends on beta. So for maxima and minima value of I2, the first derivative of I2 with respect to beta will be equal to 0, and the second derivative will be either greater than 0 or less than 0, depending on the minima or maxima conditions. Now if you differentiate this I2 with respect to beta, you get a term. So this term becomes 2 times n sine n beta into cos n beta, differentiation of this first part divided by sine square beta, minus differentiation of this lower portion, that is 2 sine square n beta cos beta by sine cube beta with a negative sign here. So this will be 2 into sine square n beta by sine square beta into n times cos n beta divided by minus cos beta, right? So you get two conditions. Now sine square n beta by sine square beta, either this will be 0 for maxima or minima, or n cot beta equal to cot beta for case of maxima or minima. Now look at how these things happens. So for secondary maxima, if you look at the picture, n beta equal to cot beta, I have take this condition. So if you put this condition in terms of in I2 expression, we will get that di2 by d beta is automatically 0 from the previous differentiation form, and obviously the second derivative of I2 with respect to beta, that is d square I2 by d beta square, this will be negative if you put this condition in cot beta equal to cot beta here, and if you put this condition here, this will give us the condition of secondary maxima, and those points for which this n cot n beta equal to cot beta are satisfied, those represent the position of secondary maxima in case of diffraction grating, right? So this is the condition of positions of secondary maxima in case of diffraction grating. Now intensity of the secondary maxima. Now if you look at the condition that n beta equal to cot beta, so if you square in the both side, you will get that in left hand side it will be n square into cos square n beta divided by sine square n beta equal to cos square beta divided by sine square beta. Now this will be, if you bring this cos square beta in this side and the sine square n beta in this side, you will get that n square cos square n beta by cos square beta equal to sine square n beta by sine square beta. Now multiply in numerator or denominator at the right hand side of this equation with n square. So we will get n square sine square n beta divided by n square sine square beta. In the left hand side, you just use the identity, that is sine square theta plus cos square theta equal to 1, and you will get that cos square n beta equal to 1 minus sine square n beta, and put in place of cos square beta 1 minus sine square beta. So you will get that n square. Now use this identity, a by b equal to c by d equal to a plus c divided by b plus d. So this will be n square into 1 minus sine square n beta plus n square sine square n beta, 1 minus sine square n beta plus n square sine square beta, and you will get this term, that is in the upper side this will cancel out, so this becomes n square, and in the lower portion this will be 1 plus n square minus 1 into sine square beta. Now for secondary maxima, this will be I0 sine square alpha by alpha square, this is due to single slit diffraction, times sine square n beta by sine square beta at this point, that is n cot n beta equal to n cot beta, and at this point we will get the value of this term becomes n square divided by 1 plus within the bracket n square minus 1 into sine square beta. So that will be I times of principal maxima, which is I1 into n square divided by 1 plus n square minus 1 into sine square beta. So as you see here, so this term is positive, and as this term is positive, because n square is much greater than 1, obviously, because n is the number of rulings within the grating element. So this will be much greater than this will be greater than 1. So if n increases, then the intensity of secondary maxima will decrease with in respect to principal maxima. Okay, so the secondary maxima in normally usually have intensity which is less than the principal maxima, as we can say from this equation. Okay, so now if n increases, what happens? If n increases, I secondary maxima by I principal maxima, this ratio will decrease. And if you increase n in a very large factor, that is several thousand or several millions lines per millimeter, then I secondary maxima becomes very weak. Okay, and if so, for large n grating, I secondary maxima is vanishingly very small. Though if n increases, then the resolving power of this grating will increase. So although the resolving power increases, it does not always meet or it is not always very much convenient to use this large n grating for measurement of unknown lambda. Okay, for monochromatic light, obviously. Now, so this is the all things about the secondary maxima. Now come to the part of secondary minima. Now, the first condition that allows us to say that this is the condition of secondary maxima, that is n cot n beta equal to cot beta. Now, if you apply the second condition, what are the conditions? That is sine n beta equal to 0, but sine beta is not equal to 0. So sine n beta equals to 0, but sine beta is not equal to 0. This gives us sine n beta by sine beta equals to 0. And in that case, intensity will be I1 into 0, so this will be 0. So this point gives me the conditions of minima. So the conditions of minima is sine n beta equals to 0. Now if sine n beta equals to 0, then n beta equals to plus minus sm, where s is the integer except those points for which s equal to 0, n twice n, mn. Now what happens if you choose this s equal to 0, n to n, mn? Now look at the condition of principal maxima, where we get a principal maxima in this case, that is a plus b sine theta equal to m lambda. Okay, now in case of secondary maxima, you look at the condition, that is n beta equal to plus minus sm. So beta equal to s divided by n into pi. So if you choose those points which is written in this here, that is 0, n twice n, the condition that gives me beta equal to integer times pi. So that will provide again the condition of principal maxima. So as we get the condition of principal maxima from this point, so that will violate the condition of secondary minima. So secondary minima are produced at those points except for s equal to 0, in, twice in, m in. So except m equal to another integer, we get this condition of secondary maxima. So condition of secondary maxima is a plus b into sine theta equal to plus minus s by n times pi, except s equal to 0, small capital N, twice n times mn. Okay, so right now, how many consecutive maxima are produced in between principal and the secondary maxima? So between two successive maxima, there are n minus 1 minima, and between two successive principal maxima, there are n minus 2 secondary maxima. So if n is the number of rulings, if you choose n equal to 5, say for example, so if you choose n equal to 5, that is 5 rulings are there for a diffraction grating, you will get the 4 minima between two principal maxima and 3 secondary maxima between two principal maxima. Now there is a term which is called the absent spectra. In some case, what happens, say for example, the principal maxima for a specific value of theta. Okay, so say for a definite monochromatic light of wavelength lambda, you get the principal maxima of order m, and if you choose the principal maxima of order m for a specific value of theta, the condition of maxima in that case will be a plus b sine theta equals to m lambda, where m is some integers. Now assume that a is such that, so you have to choose the transparent region in such a way that for a particular value of theta, sth order diffraction minima exist at the same point. Look at this part in a very careful way. First, what I say, that for a specific value of theta, we get the maxima for a diffraction grating, mth order diffraction grating. So the condition is a plus b sine theta equal to m lambda, where m is integer. That is the condition of principal maximum. Now assume that you choose a in such a way that this condition a plus b sine theta equal to m lambda will satisfy automatically for this diffraction grating, and you construct that particular diffraction grating in such a way that the sth order diffraction minima that exist at the same value of theta. So again, a sine theta equal to s lambda, that will satisfy at the same time. So at the same time, we have two such conditions. One is for principal maxima and another is for secondary minimum, right, for a particular value of theta. If this two satisfies, then those principal maxima are become absent from the diffraction spectra, right? So as the condition of that is basically simultaneously satisfaction of this condition will happens when for a particular value of theta, that is a plus b divided by a equal to s. So uh, for a definite value of theta, we have got this condition, that is a plus b divided by a equal to s divided by m, where s and n both are obviously integer, and these conditions are satisfied. So in those principal maxima will be absent from the diffraction spectra, and those we have called the definitely the absent spectra there. And there is another absent spectra are there, or sometimes happen for a uh, grating where practically there are some errors in rulings. If the error is random, that means the rulings which are random in a fashion, then what happens for the grating? If you look at this random orientation of that in slits, what you will get? You will get a general illumination in the background of the diffraction spectrum. Okay, in a very short region of diffraction maxima minima part, you will get this time of just a continuous background illumination. And if the error is progressive in nature, that means error will successively happens in the several regions, then the nature of that spectral lines become sharper in the plane which are different from the focal plane of the optical system. Okay, and that particular things happens for a diffraction getting, which are not included. I have just telling it to you, and those are called the ghost of this diffraction. And the ghost arises due to just the mechanical defect of a grating when these rulings are made in a very random way, and if we'll get the diffraction uh, uh, in that fashion, that is called a ghost. Now if you look at the intensity distribution pattern of a diffraction grating, you will see that there are two uh, uh, particular terms that arises due to grating, that is sine square n beta, that is diagram of sine square n beta, and obviously sine square beta. As this is case of sine square n beta, the diffraction happens in a very crucial way, and the intensity becomes this is the just a scaling factor 1, and the distribution of sine square in beta will look like this. So this is in beta, and obviously sine square beta, this curve will happen in this way. Okay, for a particular scale of beta. Now if you combine these two in the same part, obviously 1 by n square sine square n beta by beta square will look like this. So this is the principal maxima of order 0, that is the central maxima here, and these are the secondary maximas, and obviously this is m equal to first order principal maxima. At the left side we will get another m equal to 1, that is principal maxima, and if you progress in the same way along this s direction, you will get a plenty of principal maxima at a different region. But what happens if you go to either right side or the left side from principal maxima? The general intensity of that principal maxima of higher order, that will diminish in uh, a successive manner. So if you move from principal maxima to first order, second order, third order in this way, that is for higher order, the intensity will uh, be less than that of a principal maxima or central maxima. Now if you just compare this term here, you will look at this picture. So if you assume that this is the intensity distribution of a single slit pattern, just diffraction due to a single slit, when there are double slit, that is two slits are happen, there will be mutual interference from different part of this uh, single slit, and you will get this diffraction pattern. Under a diffraction maxima there will be plenty of interference maxima minima, and in case of secondary maxima this happens. Now there is only a single principal maxima and there are several secondary maximas are there. In practical case we can look 2 or 3 or 4 5, not more than that, because if you go to the higher order secondary maxima, in those cases intensity becomes just diminished. Okay, the intensity reduced to a regular fashion if you progress to at the right hand side or the left hand side or the higher secondary order. Now come to the part of n number of slits. What happens in case of grating? So in case of grating you are getting this kind of diffraction diagram. So this is the principal maxima of order 0, this is the principal maxima of order m, this is the principal maxima of order minus m at the left hand side, and in the right hand side you will get the secondary principal maxima of order m equal to 2, and in between these two principal maxima, that is for m equal to 0 to m equal to 1, you will get the n minus 2 number of secondary maximas and n minus 1 number of secondary minimas. Okay, so if you consider this from single slit, if you move from single slit to double slit to n slit experiment, you will get that there will be a significant change of diffraction spectrum due to the mutual interference of that rays that are coming from different opening region of the slit. Okay, now if you increase the value of this number of slit, what happens? If you use just two slits here and you draw a diagram with respect to sine theta versus relative intensity, you will get this picture, that is principal maxima and there are secondary maxima at the right and left hand side of this principal maxima. If you use three slit, what happens? This is principal maxima, there will be secondary maxima of order 0 and this is of order m, and there will be 3 minus 2 number of secondary maxima. So this is one secondary maxima and there are two secondary minima, so these are two secondary minimas are there in between two principal maxima. Now if you increase this term for 4 slits at the same time, you will get two secondary maxima between two principal maxima of order 1 and 0, and you will get 3 minima. Now move towards a slit for n equal to 5. What happens? This is principal maxima and this of order 0, this is principal maxima of order 1, and you will get 5 minus 2, so 3 secondary maximas and obviously 1 2 3 4 secondary minimas. Not only that, the intensity distribution, that is the maximum intensity of principal maxima, will change in a significant fashion. How? For single slit, let us consider that I2 is the intensity of principal maxima. Now if you use 3 slit, what happens? That will be n square by 4 into I2. Okay, so that will be, if you choose n equal to 3, that will be 9 by 4 into I2, right? Now if you choose 4 slit, that will be 16 by 4 into I2, that is 4I2. And if you consider 5 slits, then there will be 25 by 4 into by 2. So intensity increased if n, that is number of ruling, increase for principal maxima, right? So there are n number 1 n minus 1 number of minima, and obviously there are n I can write it here, that is n minus 2, sorry, n minus 2 uh, number of secondary maxima, okay, n number of n by n minus 2 number of secondary maxima in between two principal maxima. Okay, so between two principal maxima there are n minus 2 number of secondary minimas. Okay, that will happens for n slit system, right? Now if you use white light instead of monochromatic light, what happens? Okay, so you will get this term. Now what happens if you choose a white light source in place of a monochromatic light? So in case of white light, the central maxima will be white, and if you look at the first order maxima, if lambda becomes small, see another thing, that if lambda becomes small, then theta becomes small for secondary maxima. Okay, so from violet to red, red will be the further one, and this is obviously the red, this is yellow, green, indigo, blue, and violet. In case of first maxima in the other side, again the spectrum will be from violet to red. So these are rainbow, first order rainbow happens in this. And if you go to the secondary maxima, then again the same thing happens, that rainbow will be seen, but the intensity becomes diminished rather than central maxima to first to the second. So if you go to the higher order principal maxima for white light source, central maxima will be white, first order maxima will be rainbow, second order maxima will be rainbow, but relative intensity becomes less than that of second central to first to secondary maxima. Okay, so in this fashion the intensity becomes diminished, and we'll get the spectrum for a white light source if that white light source used to illuminate grating. So with this, I think I end the form of this diffraction, plane diffraction grating. So thank you.